Space is curved by Hubble sphere expansion. A round Hubble sphere expanding outwards in all directions. Under your quantum physics model, that can be stated as a foundational assumption. Space field principle. Space is fundamentally a flat, continuous field. Celestial bodies do not create gravitational wells or curvature in space. Apparent gravitational effects arise from interactions, pressure gradients, field dynamics, and motion within the space field. This differs fundamentally from general relativity, where mass energy is associated with space-time curvature. A compact mathematical representation for your model could be where phi represents intrinsic geometric curvature of the space field. Then gravity would instead be modeled as a field force or field gradient phenomenon, for example, where phi is the effective quantum field pressure/potential. So in your framework, flat space field leads to no gravitational wells, leads to celestial bodies interact with the surrounding field, leads to field gradients, produce apparent gravitational acceleration. This is a testable alternative hypothesis, but it should be presented as a proposed model rather than established physics unless experimental evidence supports it.
What if I told you that straight depends on where you stand? In regular flat space, the kind you drew lines in at school, a geodesic is literally a straight line, shortest path point A, point B, but the universe isn't school paper, it's space-time, and space-time can bend. Here's the rule. In general relativity, things not being pushed or powered don't choose a path, they reveal it. They follow geodesics, the straightest possible paths through curved space-time. From far away, those paths can look curved. Up close to the traveler, they feel straight. Think about Earth orbiting the Sun. From our cosmic balcony, it's an ellipse. From Earth's point of view, no rockets firing, no engines burning. Just free fall, the straightest line available in a warped space-time. It's not turning because it wants to. Space-time is turning underneath it. Local versus global is the key. Locally, right around you, gravity can disappear. Float inside a falling elevator or drift in a spacecraft, and you feel weightless. In that tiny patch, physics looks flat, and your path is straight. Globally, stretch the view across stars and galaxies. The same path gently bends, guided by the curvature sourced by mass and energy. You've seen this already on Earth. The straight flight from New York to Tokyo arcs over the Arctic. On a globe, the straightest route is a great circle. It only looks curved on a flat map. Spacetime does the same trick, just in 4 dimensions. Here's a twist. Geodesics don't always mean shortest distance. For massive objects, they extremize proper time, the time ticked by a perfect clock you carry. Free fall maximizes your own time compared to any powered detour. For light, the path is a null geodesic. No proper time passes at all, and even that path bends near massive bodies. That's why starlight curves around the sun. So, is a geodesic a straight line? In flat, empty space, yes, absolutely. In our real, lumpy universe, it's the straightest possible path through curvature, which can look curved from the outside. The punchline is simple. Straight is local, curvature is global. Zoom in, you find straight lines. Zoom out, you find the map itself is bent. Next time you see a planet orbit or a beam of light bend, don't think mysterious force yanking it sideways. Think that's the straightest way forward when spacetime isn't flat. Because in the language of gravity, going straight is exactly how you fall.